This is stripping torque and screw drive types from Team 9. Our team objective is to find out which screw head is the most resistant to stripping. The customer could be anybody doing any kind of handiwork of any capacity with screws. Our team wants to find out what torque is needed to strip each type of screw head to know which one would be best. A little bit of background on our problem. Screws are used in a lot of different work environments, including car, planes, and everyday items. Sometimes the wrong head type can be used and it won't be tight enough, or it needs to be a little bit looser to come out again, and it won't because it either cams out or strips. If we find a stripping torque for each screw, then the customer is able to know exactly what head type to pick for the different circumstances and requirements that they're working with.
All right, here we have our design choices. The first choice we thought of was using an electric torque wrench, and then we also considered using an impact driver. And now I'll go over the design matrices and kind of explain how we came to our decision to use the manual breaker bar and luggage scale. So we graded it based on the ability to form a governing equation, the cost, the accuracy, the repeatability, and the ease of use. And the electronic torque wrench scored really well in everything except the governing equation, because it shows the torque instead of the force, so it kind of already gave us the answer. And then for the impact driver, it did pretty poorly on everything except cost, because we already had one, and it was definitely one of the easier options to use. So ultimately, we decided to use the manual breaker bar and luggage scale because of its ability to form a governing equation, giving us that force so we could solve for torque, and the accuracy and repeatability were also a big factor in choosing this.
Okay, so we were testing the torque of different head types on screws and how much torque they could take until they either strip out or cam out. So an example of a cam out or strip would be these Phillips heads. This is where, when applying torque, the bit actually raised up, and applied more force in the upward direction than rotational force. So this is our test rig. We have an aluminum block with holes drilled and threaded in it. The aluminum block goes onto these two rods and then lowered down onto our driver. Until it slots in like that. So then we ensure that it's pressed down firmly. This rod sort of supports the beam. This rod stops the bar from twisting. This piece of wood has a hole drilled in it to support the bottom of the T handle right here, and that really reduces the movement to be only rotational rather than moving all over the place. So once the bar is set in, we take this can, which is full of BBs and weighs 1 kilogram, and we set it on top. That was our determined preload. So now when we test, if the can lifts up, that would be classified as a cam out, or if the bar slips, that would be a strip. We take our luggage scale force measurement device, hook it onto the bar, and we ensure that it is on this metal BB, which prevents it from coming off of the bar. And then as we pull on it, we want to ensure a 90-degree pull angle. So then, using a video to find the maximum, we slowly apply torque to the fastener until it either pops and strips out, or until the can lifts up. We did this to allow there to be a proper amount of preload easily on top. That's why we have the bar set up as we did. And we have the hole, again, to reduce motion to only rotational.
Here are the results from our testing. As you can see, 10 different tests were performed for the Phillips drive and the Allen hex drive. Those tests gave us a reading back of a mass, converting that to newtons and multiplying it by the moment arm of 0.21 meters. We were able to get a torque. We were not able to do testing for the slotted, as that bit snapped on the first screw, showing us that it is a very strong head, but it is subject to the bit snapping. We were also not able to perform it for the Tex head screw, as the screw head snapped right off of the bolt twice. This showed us that while the other ones were able to get readings, that the Torx head screw is definitely the strongest. Based on that, if you need something to be tightened all the way, that's obviously the one that you would want. The Phillips head is not the best option, as it is subject to camming out very easily. And the slotted is good about not stripping, but is the last choice because the Allen also performed very well, having a much higher stripping torque than the Phillips. This is very consistent with our theoretical, as everywhere that you look, you can see that Torx heads and then Allens are the most likely to be used to resist stripping.
Hello, my name is Christian Barr. I'm a mechanical engineering student at USU, and I'll be going over the uncertainty, and this is everything I'll be going over. Calibration was done for the digital caliper and force tester. The R-squared value for both was near 1, which shows that they are accurate compared to a known standard. This is the data from the force tests, and this is the link for the force tests. Chauvenet's criterion was checked for the Phillips drive and the Allen drive. The Phillips drive was found that the 24 Newton meters was an outlier, while that for the Allen drive, the 29 Newton meters and 29.2 Newton meters were identified as outliers. The chi-squared test is not appropriate since 10 points are needed for that test, and the Phillips test only has 9 points, and the Allen only has 8. Shapiro and Wilkes test is better, since that's for a sample size greater than 3. Hypothesis testing was done for the Shapiro-Wilkes test. The null hypothesis was that the probability of normal distribution P is greater than or equal to alpha. In both cases, P was greater than or equal to alpha, which shows that the null hypothesis is satisfied and the sample may have a normal distribution for both the Phillips and Allen drive test. This is where P was found, the link for the Shapiro-Wilkes test. This is the uncertainty for the force data, using the measured variables, force, length of the moment arm, and angle. This is where the precision uncertainty was found, links. The torque uncertainties for the Phillips and Allen tests were found to be plus or minus 0.1 Newton meters, while the torque at a 95% confidence interval for the Phillips test was found to be this, and the torque at a 95% confidence interval for the Allen test was found to be this. What that confidence interval analysis shows is that 95% confidence, the true mean for the strip torque of a Phillips screw with an M6x1 drive is 16.89 to 18.93 Newton meters. While for the Allen test, the true mean for the strip torque is between 18.19 to 19.47 Newton meters. The theoretical value for an M6x1 screw was found to be 20.3 Newton meters. The Phillips screw is off by 11.8% of that value, while the Allen screw is off by 7.2% from the 20.3 Newton meters. The strip torque could deviate since the screw bit could translate left and right, and the actual screw was tightened before tested, so that could deviate from the value. And now Hagar will go on with the conclusion.
So in conclusion, the Phillips head performed the worst and was pretty unreliable under even light loads and would cam out pretty quickly, which led us to the conclusion that Allen head screws were the best option, as they perform the best under higher loads and very rarely stripped. We also tested Torx and slotted screws, but both of those destroyed the bit before any deformation, so the tests were pretty inconclusive.